All right. So if you guys remember, if you have a capacitor hooked up to a voltage source, if this is my time and this is my voltage across the capacitor, initially, when there's no source, it's going to be 0, but it's going to rise up, rise up, rise up like this, a first order system. All right. Okay, so our question says our capacitance is 100 microfarads. So V of phi is just voltage at 5 seconds or 5 units. So voltage at after 5 seconds is 10 volts. So if I have 5 seconds, this is 0 and this is 5. So at 5 seconds, my voltage is going to read 10 volts. And initially it's 0. So find the charging current. So now we got to find what is the current. So let's go ahead and write down the formula for that. So if you remember, you have to keep going back. I wish I had this written down. So this is the formula that we're going to use. Let me rewrite that in a much neater way. So V of t is VC, it's the capacitor voltage at 0 plus my capacitor integral 0 to t current tau d tau. So this is 10 volts and my voltage at 0, so it has no initial charge, so it is 0 plus 1 by C is 1 by 100 microfarad. All right, so this, if you solve, I'm not going to do this, but if you solve the integral term, you would get I of t times t. So this would be I of t times t. Very simple. So here our t is 5 seconds. So it goes from 0 to 5. So if I just substitute that here, I would get my I of 5, which is what I want to know, which is what is the current at 5 seconds due to the flow of charge times 5 seconds. So just rearranging the terms, I'm going to keep my I of 5 where it is. I'm going to write IC of 5 is, so the 100, the C value goes to the other side, so that's going to be 10 power minus 3. 1000 times 10 power minus 6 is 10 power minus 3 divided by 5, so that's 1 by 5 is 0.2. I'm going to keep 10 power minus 3 as it is, so it's 0.2 milliamperes. Very simple. All right, so just we might look at this part in the future videos, why the current flows in this, and it follows a certain set of rules. But for now, you just have to know how to use this formula. And remember, this integration sometimes can be tricky, but if it's not tricky, just remember it's current times t. Current at time t times t. So another easy way to look at it is basically the value in the blue box is our charge, right? So this is our charge. So charge over time is current. So our charge would be current times time. So that is what we're doing. That is what we're trying to find out. All right, let's go to our next problem. All right, guys, so here our objective is we got a bunch of capacitors in this network, and we got to find out what the equivalent capacitance is. So the rule for capacitors, so if you have resistors in series, you add them. So for a capacitor, it's the opposite. So if you have capacitors in series, if you have capacitors connected end to end, your equivalent capacitance, the inverse of equivalent capacitance is equal to the sum of inverses of your individual capacitances. And if you have branch capacitance, sort of like this, it's just the sum of the individual capacitances. So all we gotta do is remember it is the opposite of resistance. So I'm gonna start slow. I'm gonna start with this branch right here. So I'm gonna solve this branch. So these are in branches, right? So if they're in branches, we just add them up. So our circuit is gonna look somewhat like this. I'm gonna rewrite this. So it's gonna have the, okay, so I've redrawn what we have in the orange box here. So 1 plus 1 is 2 microfarads. So that's our 2. Now all 3 of them are in series. So my equivalent capacitance would be 1 over 1 plus 1 over 2 plus 1 over 2 microfarad. That's very important. So if we solve this, it's going to be 0.5 microfarad. So that's our equivalent capacitance. So another shortcut way of doing this is if you have 2 capacitors of equal value in series, because we are doing the inverse, so equivalent capacitance is going to be half of that. So if I take the equivalent capacitance of just these 2 equal capacitors, it's going to be half of 2. So that's going to be 1. And now I have 1 and 1. So if I take 1 and 1 capacitors in series, so it's going to be half of 1. So that is my 0.5 microfarad. All right, so just remember those basic rules and you're good to go. So pretty much when it comes to capacitors, these are all the things that you can get asked in the fundamentals of engineering. Let's run through them real quick. So we got a capacitor's parallel plate, and it's a way of storing charge. And we have 3 basic formulas, very important to remember these, and one relating charge with voltage, one relating energy with voltage, and one relating voltage with current. And we have our applications in rectifiers, in ripple correction, power factor correction in giant facilities, and also many other applications. And we had our problems on parallel plate capacitor. So again, very important, just remember the capacitance of a parallel plate capacitor is epsilon times A by D. So if you want to increase the capacitance, you increase the area or minimize the distance. Just some basic math relations. And yes, do not touch a capacitor. It can have very large voltage on it. And if you have a time-dependent source, the charge on the capacitor is also going to be varying with time, and the energy is also going to be varying with time. And yes, so this is the way the voltage changes with current or with time, and because the voltage is changing, there's going to be a current. And lastly, the rules for finding the equivalent capacitance. If they're in series, you follow same rule that you would follow if resistances are in parallel. And if they're in branched, you just add the capacitance together. All right, guys, so that's it. Good luck. If you're taking your fundamentals of engineering exam, it's going to be an easy section on capacitors for sure.